Okay, now I'm going to talk about state feedback control. So we've already discussed PID as a proportional integral differential control, and it can be very successful. And it's particularly good for systems with one input and one output. It's not so good when we have more than one input and we have more than one output and when they're coupled together. Now the thing that this kind of analysis does when you're using things like Laplace methods and you're using PID control is we're only really interested, or we're only representing input-out relationships using that kind of technique. Now what state space methods will let us do is it will first of all, it'll let us deal with multiple inputs and multiple outputs that can also be coupled, which is a big deal. And it sort of gives us a bit more principled ways of actually doing analysis rather than just fiddling with things, which is a bit what we do with PID control. So what we need then are more rigorous mathematical methods, and state space models are a description, a full description of the state dynamics using state variables. And basically, you know, they can also represent things that's going on in the system that we don't actually see from the outside. So it can, you know, we can take into account hidden states that we normally wouldn't be able to capture with transfer function models. We can actually represent then systems using matrix notation doing this kind of analysis, matrix notation, and we're going to analyse them using linear algebra. And this is going to support multi-inputs and multi-outputs. It lets us also deal with time-varying systems. In particular, though, we're going to look at the situation where we can deal with non-linear systems. So what we're going to do is we're going to say you've got a system which is intrinsically non-linear, but we can linearise it around certain points. And quite often you'll do that around the equilibrium points. So what kind of things can there be in a system that you can't actually see from the outside? Well, it could be that there's, you know, you can't measure something, for example. You couldn't measure the velocity. You've only got a position sensor or something like that. This also lets us control things that we couldn't otherwise control. And it lets us, if you like, create observations of things that we couldn't normally otherwise see. And it can be built up in an optimal and robust framework as well. So before we jump into state space models and state feedback control, let's just remember what we do with output feedback control. And, you know, why do we need control at all with feedback? And it's because if we have a plant and we're not quite sure of its characteristics, then we can't just build a feed-forward controller which will work all the time, because we have to generally know what the characteristics of the plant are in order to do feed-forward operation. In addition, if there's disturbances, you know, like you've got something that's actually disturbing what's happening. If it was a robot arm and it was moving and there was sort of something a bit in the way, unless you're actually looking at what the output's doing, you can't compensate for that kind of thing. So that's why we use, in the first instance, output feedback control. We just look at the output, feed it back to the input and generate an error signal, and on the basis of that we can actually have this closed loop controller. But this is only looking at the output. It's not looking at the full state of the system. So full state feedback control means exactly that. We actually use the full state of the system, and basically we can capture the control element by saying the input now is going to be a scaled version of the state. So we're going to say that the input u equals minus k times x, where k is going to be a weight vector of the gains, and x is going to be a state vector of the system. And of course we can also incorporate into this arrangement a reference input for each of the states as well. So if we originally start off by considering what the state space model looks like, that's the parts of this diagram in black. That is our that's basically our signal flow graph for a state space model. And what we see now, we've added in this u equals minus kx pathway. So we now, I shan't go through what we were doing before for the state space model, but basically we're tapping off the state x here, and we're passing it through gain vector minus k, and then we're feeding that back to the input here. And like I said, there's a control input which can be 0 if that's the basically the reference we're actually trying to achieve. But we're feeding back now the full state. We're not feeding back from y from the output. Y could only be a slight representation of what's going on inside the model, whereas if we have x, the full state of the system, then we're feeding back as much as we possibly can. And that's got some very nice, elegant properties when we start doing that. So let's look at what the state space equations become when we actually use state feedback control. Right? So we start off by using our standard equation, which you really need to know off by heart. X dot equals ax plus bu, where x dot is the derivative of the state vector, a is the system matrix, x is the state vector, b is again another vector, and u is the input. If we substitute in u into the first equation equals minus kx, then we get the second part here, ax minus bkx. And what we do then is factor out the x. And then we see we get the expression a minus bk times x. We can do the same thing for the output equation. It started off as cx plus du. It goes to cx minus dkx. And we end up with the expression then y equals c minus dk multiplied by x. Now if we now look at the system, the first equation for the derivatives of the state derivative, the x dot expression, x dot equals a minus bkx, what we see, well, first of all, we haven't got the bu term, obviously that's been incorporated, but effectively what we've got is something which looks like the x dot equals ax expression, except rather than having an a, we've got another matrix, a minus bk. So we can immediately look at this and then we can say, well, if in the original expression stability depends on the eigenvalues of a, now we can say the stability has got to depend on the eigenvalues of a by minus bk, since that is the effective new a that we get by using state feedback control. Consequently, if we want to look for the eigenvalues, we need to calculate the determinant of the matrix lambda I minus, open brackets, a minus bk, close brackets, equals 0. What we can also see from this expression is by changing k, we can actually change the location of the eigenvalues that we're going to get. And that's exactly the trick that we're going to use. We're going to change the gain matrix k, or the gain vector k, in order to put the poles of the system where we want them to be. So in an open loop system then, just to summarise, x dot equals ax plus bu, y equals cx plus du. Stability is determined by, of course, the eigenvalues, the poles, which are the eigenvalues of the matrix A. In a closed, or related to the eigenvalues of the matrix A, in a closed loop system, we have the expression x dot equals a minus bk times x, y equals c minus dk times x. Stability now is related to the eigenvalues of the matrix A minus bk. And in state feedback control systems, we know that now, because we got this k in there as well, choosing the value of k lets us put the eigenvalues or the poles of the system where we want them. If everything goes well, it does. So basically, we need to be able to say, where do we want the poles, the eigenvalues to be of this system now, and how do we find k in order to achieve that? And this is not necessarily trivial. There's a couple of simple ways of doing it. Really, the easiest way is, well, there's several ways. We're going to use pole placement, but we could also use optimal methods, optimality criteria. That's what we will do when we discuss optimal control. But we're going to look here at pole placement, and we can do this by hand if we wish for small tiny systems. So the kind of systems you're going to be doing in the exams are going to be that kind of system. And we need to choose K, right? So generally speaking, we have negative real parts to the eigenvalues, right? We don't want anything to go unstable. So to do so, we need to solve the characteristic equation then. The determinant of A minus BK minus lambda I equals 0. We can also do this all in automatically in MATLAB using the place command. So I suggest most of you have done that. You can have a look at it again, look at the help on that. Let's have an example now where we're actually putting poles by hand by just basically working through the equations. This is an old exam question, but this is a typical kind of a question, and the typical kind of explanation that you're going to get now is, how do you actually find these gains by hand? So we've got our system with an A matrix 0, 3, 2, 1, and we've got the B 0, 1, and we've got an output term. What the question is now is to basically design the state controller. So in other words, find the gains K1 and K2. So how do we find K1 and K2? Okay, let's start at the beginning. State space equations take the form x dot equals ax plus bu, y equals cx plus du. And these are the system values that we've been given. We've been given A as 0, 3, 2, 1, B equals 0, 1, and C equals 1, 0. We're now going to apply state feedback, setting u equals to minus kx. And K is going to be this. It's going to be this gain matrix, right? So it's going to effectively be a row vector K1, K2. We want to know the particular values of the two elements, and we're going to calculate the effect of having this state feedback control. So we substitute in u equals minus kx into ax plus bu, and just like we showed just now, x dot then becomes ax plus bkx, which we factor out to be x dot equals a minus bkx. And the stability is now determined by the location of the poles, right, of the matrix A minus bk. So to find the eigenvalues of that expression, right, we have to work out the determinant, or solve the determinant A minus bk minus lambda I equals 0. So let's now look at that equation and put, first of all, in the values that we've got, right? So we've got the B and the K, right? So let's calculate the BK component, and that's going to be 0, 1 times K1, K2. Now don't forget, we're going to calculate A minus BK. So that means we're going to take something away from A, which is the BK part. Therefore, we can immediately say we know the dimensionality of the BK, B times K, has got to be the same as that of A. In this case, it's got to be 2 by 2. So if you're a little bit confused and you forget how to do the multiplication of the B and the K, remember what you end up with when you do the multiplication has got to be the same dimensionality as the A. So that basically means this has got to be, the result's got to be 2 by 2. So that the way you do that is you multiply 0 by K1, 0 by K2 for the top terms, and then 1 by K1, 1 by K2 for the second row. Right. Now we're going to look at our equation that we've got to solve, determinant A minus BK minus lambda I equals 0. We're going to stick in all the values and see what we get. So we stick in the A, we stick in the minus BK, and then the minus lambda I. Then what we've got to do is just go through and evaluate by element subtraction. So 0, take away 0, take away lambda minus lambda 1. Well, we're just putting it as lambda 1 in this particular case. In fact, it should be lambda. This term goes to 3, take away 0, which is 3. This one is 2, take away K1, take away 0, so 2 minus K1. And here is 1 minus K2 minus lambda, right? So we end up with this simplified version. And we need to calculate the determinant, and we know for 2 by 2 with A, B, C, D, it's going to be AD take away BC. So we can then work out the characteristic equation. It's going to be minus lambda times 1 minus K2 minus lambda minus 3 times 2 minus K1, and that's got to equal 0. And that's the characteristic equation, and if we solve that, well, basically that will give us what the lambda is. But as we can see, it depends on what the K1 and the K2 is. So what we want to do now is we want to say, well, we're going to aim for some location of the poles, and we're then going to choose the K1 and the K2 so we get them. So first of all, let's simplify that a little bit, and probably what you need to do is multiply it out as much as you can. So we multiply it out, we end up with lambda squared, and we factorise things out as much as we can. Lambda squared, lambda K2 minus 1 plus 3K1 minus 6 equals 0. Now, what we've been asked to do is to find poles, or set the poles at minus 3 and minus 2. Right? So we want to work out what the values of the gain, K1 and K2 are, such that we end up with a system with eigenvalues at minus 3 and minus 2. But we can immediately say, well, actually we can write down the characteristic equation of a system which has got those two eigenvalues. That's quite easy. And the characteristic equation is going to be lambda plus 3, lambda plus 2 equals 0. We multiply these things together, and they've got to equal 0, right? And we can multiply that out, and we end up with lambda squared plus 5 lambda plus 6. And here's the nice bit. All we have to do now is to say we're now going to compare coefficients on what we want the characteristic equation to look like, which is this, and compare them with the actual characteristic equation that we've got, right? So that has got to be equivalent to that. So our lambda squared plus 5 lambda plus 6 has got to be equivalent to lambda squared plus lambda K2 minus 1 plus 3K1 minus 6 equals 0. So we can immediately look at that and say, well, I can immediately say that, right, 5 equals K2 minus 1 because we can compare coefficients. Therefore, K2's got to be 6. And then we can say, right, well, 3K1 minus 6 has got to equal 6. So K1 has got to equal 4. So the feedback law then is going to be minus 4x1 minus 6x2.